Now we have new problem. A hollow steel shaft with an outside diameter of 400 mm and an inside diameter of 300 mm is subjected to a torque of 300 kN as shown in the figure, this one. And the modulus of rigidity or shear modulus for the steel is 80 gigapascal. The maximum shearing stress in the shaft, so this is the first question. The second question is the shearing stress in the transverse cross-section at the inside surface of the shaft, and the magnitude of the angle of twist in a 2-meter length. Okay, so if we try to draw our figure again, now we have torque here that is 300 kN. No, and since using the right hand rule, okay, the double-headed arrow here, that is 300 kN, that is the torque. Since our material is hollow steel, so we have hollow in between, then we have our outside diameter that is 400 and our inside diameter that is 300. So we compute for the maximum shearing stress in the shaft, that is from the formula we have the maximum shearing stress, the internal torque times the R over the J. This supposedly be our rho, okay, that is the distance from the center to any point, okay, but in the case of maximum shear, our rho is equal to R. So that is where the location of our maximum shear, outside or on the surface or in the outside surface of our circular bar. So that is our R here. So we have a torque here, and now our torque here, or that is the internal torque, that is equal to the external torque, that is 300 kN. Since if we cut in any section of this point, our internal torque is basically equal to the external torque. Okay, so we have here 300. Now take note, since this one is in kilonewton and this one is in meters, so we multiply this by 1000 to get newton, and this one multiplied by 1000 to get millimeter. So therefore we have 1 million. We multiplied it by 1 million, or it's just 10 raised to the 6. So we multiply 10 raised to the 6 so that we could have a unit of Newton millimeter times the radius, since again our maximum shearing stress occurs at the outside surface of our circular bar. So therefore our rho here, that is the radius from the center. So we have our R, that is 200, that is in millimeter, over the polar moment of inertia. Since this is hollow, so we get the outside polar moment of inertia, or the polar moment of inertia of the greater circle, then minus the polar moment of inertia of the hollow. So that gives us simplest form, that is pi over 32 times the outside diameter raised to the fourth, that is 400 raised to the fourth, minus the diameter or the inside diameter, that is 300 raised to the fourth. And we have unit here that is in millimeter raised to the fourth. So our answer here is in terms of Newton per square millimeter, since if you multiply these two, you can get millimeter squared, correct? So you can cancel this out, and you can cancel 4, then the remaining would be 2. So you get a unit of Newton per square millimeter. That is our maximum shearing stress, that is equal to, we have 34.92, that is we have Newton per square millimeter, or that is in terms of megapascal. So this is the maximum shearing stress in the hollow steel shaft. And question letter B asks for the shearing stress on a transverse cross-section at the inside surface of the shaft. So we have question letter B, that is the stress at this section, or at this surface here, inside section. So therefore, we have our shear, that is the internal torque times the rho over the polar moment of inertia. That is, we have our internal torque that is still the same, 300 times 10 raised to the 6 times the rho. Our rho here is the radius of the inside circle. So at this point, so this is our rho. Since we are looking here for the stress in the inside section. So at this point. So therefore, our rho is the radius of 300, that is 150 millimeter, over the polar moment of inertia is pi over 32 times 400 raised to the 4th minus 300 raised to the 4th, and our shear here is equal to 26.192, that is in megapascal. So this is the shear stress in the inside section of the hollow steel tube. And then we have example here, letter C, the magnitude of the angle of twist in a 2-meter length. So we compute for the angle of twist, that is letter C, we have the angle of twist, that is, we have the formula of the angle, that is TL over JG. And we have the torque here, the internal torque, that is 300, that is times 10 raised to the 6, times the length. Since we have 2-meter length, they have 2000, that is in millimeter, over the J. Since again it's hollow, that is pi over 32 times 400 raised to the 4th minus 300 raised to the 4th, okay, times the shear modulus, that is, since this one is steel, then we have our shear modulus of rigidity here, that is 80 gigapascal. So we have 80 times 10 raised to the 3, and we have unit here, that is, this one is in term of Newton millimeter, this one is in millimeter, this one is in millimeter raised to the 4th, and this one is in Newton per square millimeter. We can cancel square millimeter here, and we can cancel 4, so the remaining would be 2. But take note, we have a millimeter squared here. If we multiply this millimeter, so we can cancel this out. Okay, and we have Newton and Newton, so therefore our angle here is unitless. So it is safe to say that our theta here is in radian. So we have the angle of twist, that is 4.365 times 10 raised to negative 3, or that is 0.004365, that is in radian. So this one is the angle of twist when we have 2-meter length steel hollow tube. I have here another example. We have a shaft composed of a segment AC. We have a segment CD. We also have a segment DB. And these are fastened to rigid support. So this one here, support A and B, as shown in the figure. Now for bronze, this one has a 35 gigapascal, that is the shear rigidity or modulus of rigidity. Then we have the aluminum, that is 28 gigapascal, the shear modulus of rigidity, and the steel has shear modulus of rigidity, that is 83 gigapascal. So determine the maximum shearing stress developed in each segment. So we compute the shearing stress in every segments in the shaft. So the first thing we do here is first to compute for the internal forces. However, we do not yet have a value of our torque. Okay? Our twisting moment, since we have TB here, so this one is, let's say that is our torque D, torque C, and we have the twisting moment at A. However, we could have two possible ways in determining this value of internal twisting moment. So the first thing we do here is we could use by cut section, cutting every segment and using equilibrium to compute for the twisting moment, or else we can use a torque diagram. Since we have given here the direction of the rotation of our twisting moment, okay, so we can create a torque diagram to this one. However, we have to convert this rotation into a double-headed arrow so that we could best internalize our diagram. So how are we going to convert this into a double-headed arrow? So we use right-hand rule. Now, if you do not know what is a right-hand rule, I have a demonstration in my previous video, the first part of this video. So for right-hand rule, if we curl our finger about the rotation of this axis or of this bar, we could have our thumb or right thumb here pointing to the right. We have our double-headed arrow represents for this rotation here or for this twisting moment here as pointing to the right. So that is our TB. Now similarly, twisting moment at D, we apply again our right hand rule to this one, and we see that our thumb here is pointing directly to the left. So we have our twisting moment at D represented by a double-headed arrow that is pointing to the left. And it is similar with our twisting moment at C that is still pointing to the left. That would be our twisting moment at C. And our A here, it is the same as with our twisting moment at B that is also pointing to the right. This is our twisting moment at A. Okay, so we have already now the direction of our double-headed arrow as representation to our twisting moment. So we could now create a torque diagram. So our goal here again is to compute for the internal torque in each segment in our shaft. Let's start with the right side here. We have torque that is the twisting moment, TB, that is, we know that it's pointing to the right. So we have to plot our TB here that is above in our actual diagram. So again, all the twisting moment within B to D is equal to TB. So that is, we have TB there. Then after that, we go downward since we have TD or the twisting moment D that is pointing to the left. So we have at this point, okay, that is TB minus TD, since we have negative magnitude for TD. But we do not know yet whether our point TB minus TD would be at this point or otherwise above the point, since we do not have known yet the value of TD, whether TD is greater than our twisting moment of B. In that case, if our TD is greater than our TB, then most probably our point here would be this at this point, or the location of our internal moment. But if our TB is greater than our TD, then our diagram will just end here at this point. Let's assume na lang that our TD here is greater than TB, so our diagram is below the reference line. Now, so therefore, this one, the magnitude of this one is TB minus TD. Now, since we have a given value for TD here that is 700 Newton meters, so we can substitute TD here as 700 Newton meters. So therefore, our internal moment here is TB minus 700. Now, at this point, we have our twisting moment C that is also pointing to the left. So therefore, we still go downward below the diagram. So we have here that is the magnitude of this internal torque that is TB minus 700, and the value of TC here that is equal to 300 Newton meter, that is minus 300. So our internal torque here is TB minus 1000. Okay? Then our TA, our last internal torque, which is pointing directly to the right, so we have positive magnitude of TA, so we go back upward. Okay, so we end at 0. Okay, so we have now computed the internal moment. So internal twisting moment here, that is in this point here we have TB. Now for C to D we have TB minus 700. And for the segment A to C, we have TB minus 1000. So first, in this problem, we have to compute for our TB so that we could have the value of this internal moment. But how are we going to compute for TB here? So we have to apply compatibility equation. Okay, so we have to introduce new equation that involves angle or the twisting angle here. Now take note, since we know that our point A and point B here are fixed support, so therefore our joint A and joint B here will not move. They don't have a angle of twist. So therefore, if we try to compute for the angle of twist of B relative to A, that would be equal to 0. Since our point A and point B are on the same reference line, even though we have twisting moments in between or within the shaft. So how to compute for the angle of B relative to A? That is just basically the summation of all the angle of twist. This equal to 0. So we have the angle of twist for C relative to A plus the angle of twist of D relative to C plus the angle of twist of B relative to D. Okay? So let's try to compute each angle here. And the angle of twist formula is we have TL over JG, in which our T here, that is the internal twisting moment or internal torque. Our L here is the length of the segment. Our J, that is the polar moment of inertia. And G here, that is the shear modulus of rigidity. So the first angle here, that is the angle of twist of C relative to A. So we have the formula, we have the internal torque that is in between C and A, that is TB minus 1000. Now take note, our twisting moment here is in terms of Newton meter. So therefore, we need to convert it into Newton millimeter. So we multiply 1000. And then we have the length of our AC, that is 2000, over the polar moment of inertia, that is pi over 32. And then the diameter, that is 25 raised to the 4th, times the shear modulus of rigidity, that is 35, times 10 raised to the 3. Plus, now for the angle of twist of D relative to C, we have the internal torque in between C and D, that is TB minus 700, times 1000, again to convert into Newton millimeter, times the length in between, that is 2000, over pi over 32, times the diameter of DC, that is 50 raised to the 4th, that is the polar moment of inertia, times 28 times 10 raised to the 3. Now lastly, we have T, the internal torque in between D and B, that is TB alone, times 1000 to convert into Newton millimeter, times the distance, that is 2500, over pi over 32 times the diameter 25 raised to the 4 times the G, the modulus of rigidity, that is 83 times 10 raised to the 3. And we know that this should be equal to 0. So we can now compute for TB here. If you want to simplify it further, we know that we could cancel pi over 32 here, and pi over 32 at this one, since this equation equates to 0. So for further simplifying it, so we could come up the answer of our twisting moment B, that is equal to 657.031, that is in Newton meters. Okay, so we can now compute the internal twisting moment by substituting this TB here, the value of TB, to every the formula of internal twisting moment for every segment. Okay, so we have at this point the twisting moment in between D and B, we have TB. Since we only have TB here, so therefore we could say that our twisting moment here is 657.031, that is in Newton meter. Now in between C and D, so we have TB minus 700, so we have 657.031 minus 700, we have negative 42.969, that is in Newton meter. So our assumption that our internal moment here is negative is correct. It's negative 42.969. So if this one is positive, then our actual diagram is incorrect. So our value here should be above our reference line, above of our datum. For this one here, we have TB minus 1000. So we have 657.031 minus 1000. This gives us the value of negative 342.969 Newton meter. So we have here negative 342.969, that is in Newton meter. So we can now compute the maximum shear stress in each segment. So let's start with the maximum shearing stress for member AC. Now the maximum shearing stress, we have the twisting moment times the radius over the J. Okay? Since our maximum shear occurs on the outside surface of our bar, and that is R distance from the center, or our rho here, that is equal to the radius. So we have the twisting moment of AC that is 342.969. So we multiply it by 1000 to convert it into Newton millimeter. Then we have the radius of our bar AC, that is 25 divided by 2, or that is 12.5, over pi over 32 times our radius, times our diameter rather, that is 25 raised to the 4. So our maximum shearing stress is equal to 111.791, since our unit is in Newton per square millimeter. So therefore we have 111.791, that is in megapascal. So this one is the maximum shear stress for member AC. Now for member CD, we have the maximum shearing stress is equal to the internal moment, or the internal twisting moment in between C and D, that is 42.969 multiplied by 1000 to get Newton millimeter, times we have 50 divided by 2, that is 25, that is the radius, over the polar moment of inertia, that is pi, over 32 times 50 raised to the 4th. And this gives us 1.75, that is megapascal. So this one is the maximum shear stress or torsional shear stress in between C and D. Now lastly, we have DB, the member DB, we have the maximum shear stress is equal to, we have the internal torque, that is 657.031, that is we have 1000 times the radius 25 over 2 over the polar moment of inertia, that is pi over 32 raised to the diameter, that is 25 raised to the 4. So we have our maximum shearing stress for DB, that is equal to 214.159 megapascal. So this is the maximum shearing stress in member DB. So this ends our last example for this lesson, torsion. And if you have questions, you can comment it down. And for more videos, please don't forget to like and subscribe. Thank you so much for listening.